Okay, dear students, welcome to my next lecture number 3 on coordination chemistry. I hope you are following the first and second lecture you followed, and I have discussed about different ideas in coordination chemistry, coordination or complex compounds. And I have already told in the last class about different kinds of ligands that are responsible for the formation of coordinate compounds or complex compounds, whereas the central metal, how it is attached or linked with the ligands and all discussed. Means usually we will take M as the metal symbol, L as the ligand symbol. So metal ligand bond also we have observed, that is a coordinate covalent bond. In this session we are going to talk about coordination number. We are going to talk about coordination number. Not only that one, how to calculate the oxidation number of central metal, oxidation number of central metal, as well as we are going to talk about coordination polyhedron, and finally we are going to speak about most important point in the coordination chemistry regarding the metals is E.A.N, effective atomic number. So these are the things we are going to discuss in detail in this lecture number 3. First of all, when you are speaking about coordination number, like in solids, we have clearly explained about what is the coordination number in a solid. Means number of nearest neighboring ions or atoms in solids, how we discussed. In the same way, the coordination number in complex compounds can also be defined as the number of atoms, ligand atoms, which are attached around the central metal in the complex compound. So I can say what is exactly the coordination number now for a complex compound which is given to us. Most of the complex compounds, whereas central metal is linked with ligand atoms. So how many ligand atoms are there around the central metal? That number is called as coordination number of the complex. For example, I am writing 4 ligand symbols like this around the metal, like this, indicates that the coordination number of this metal atom or ion in the complex is said to be 4. Means what is coordination number? Coordination number is number of atoms of ligands linked with the central metal, via coordinate bond or dative bond. It's very simple and all these things. For example, if you directly taken CuNH3 4 times 2 plus complex ion or coordination ion. So in this ion, what is the coordination number of copper asked? It's very clear that we have 4 NH3 groups are there. NH3 is ligand here in this. This NH3 number attached to the copper is 4. This 4 is called coordination number of copper. So here, what is the coordination number of copper metal? That is 4. While that of one more example, if you take CO, E.A.N thrice 3 plus ion you have taken, but here E.A.N is called bidentate ligand, means Here in the case of bidentate ligand E.N, we have to be very careful. Such kind of ligands will have two donor atoms, means one ligand is said to contribute towards the coordination number by two numbers. That means coordination number of the bidentate ligands, when we are observing here, the number of bidentate ligands into 2 will be the answer of coordination number of this complex. Coordination number of cobalt in this complex is 6. The reason behind that one is around cobalt there are 6 nitrogen donor atoms are there. That is the coordination number of this cobalt complex. Hope you have observed this one. Means we should be very careful about the type of ligand also attached to the central metal in deciding the coordination number of the complex compound or complex ion. Hope you observed these two examples. You have got a clarity in this one. Now I am going to just give you most common coordination numbers of this subject. Most of the metals are there that are transition metals exhibit 4 and 6 coordination numbers. So what are the commonly observed coordination numbers in our discussion? They are 4 and 6 by the transition metals, because they themselves act as central metals in the coordination compounds. Now we will have some different examples. Once again we will see the examples of the coordination number of the complex ions. For example, if they are given a complex ion, complex compound K4 FeCN6. So what is the coordination number of this central metal ion, central metal iron? How much? Means we should be very careful in observing how many ligands are present around the central metal. That number only. Here CN is a monodentate ligand, so the number of coordination number of this metal is 6. Monodentate ligands are there, means coordination number is same number. Okay. Sometimes what will happen, we will be having two things, that means different ligands are present. You will see example, NH3 4 times Cl2, PT NH3 4 times Cl2 given. So here ligands may be different, number of ligands which are present around the central metal may be different, but the coordination number can be calculated by considering all the different types of atoms around the central metal. We have 4 NH3 groups are there, so 4 is the coordination number contributed by ammonia, and Cl2, 2 chlorines are there, so 2 is the coordination number contributed by chlorine atom. So total is how much for the platinum in this is 6. So coordination number of platinum in this complex is 6. So here we have 4 observed, here we have 6 observed, because only the thing we have noticed is E.N is nothing but bidentate ligand. So what is E.N? E.N is a bidentate ligand. So bidentate ligands are there, means definitely we should be very careful in calculating the coordination number. Means irrespective of the monodentate or bidentate, how we can define coordination number is nothing but number of atoms attached to central metal via coordinate linkage, coordinate bonds. So that is the answer for this coordination number definition. Some of the heavy metals are there, they may exhibit more than 6 as the coordination number, like zirconium, tantalum, as well as neodymium. Best examples are there, but these are the frequent examples we will come across in our syllabus. Okay, this is what about coordination number. You can see the different examples. Now we will talk about the next one, that is oxidation number. So this and all, oxidation number is also one of the important characteristic property we have to learn in the coordination chemistry for central metals, oxidation number of central metals. Okay, let us talk about the oxidation number. Oxidation number of central metal. Oxidation number of central metal in the coordination complexes. So when we are talking about oxidation number will be exhibited by central metals. Those metals usually they will exhibit oxidation number in their normal salts. The same kind of oxidation number will be exhibited by the central metals in the complex compounds. Is the common behavior of this metals, transition metals in the coordination complexes. For example, when you are talking about oxidation number, it is a kind of charge, means some of the coordination complex ions they will give in the exam. Okay, they will ask you to find what is the charge, what is the oxidation number of central metal. Means oxidation number of central metal will be charge a positive value, and that positive value will be obtained by using a mathematical expression. Okay, so that you can take it as charge on the complex ion. Charge on the complex ion is equals to oxidation number of central metal, oxidation number of central metal plus charge on the total charge on the ligands, total charge on the ligands. In this way we can understand the charge on the complex ion, some of the complex ions if they are given. Okay, so what is the oxidation number? So oxidation number of central metal which is equals to charge on the complex ion, charge on the ion minus charge, total charge on the ligands, minus total charge on the ligands. Hope you understand oxidation number how to calculate. Means if they have given a complex compound, completely a neutral complex compound, from that also we can get complex ion, or we have to take an example of charged complex ions to discuss about the oxidation number. Okay, for our general idea I will give you a complex compound K4 FeCN6. So how it ionizes in the aqueous solution is, that means it produces 4 K plus ions and one complex ion, that is FeCN6 times 4 minus. Got it? Now if you take, this is the complex ion example, that is FeCN6 times 4 minus. In this complex ion, your aim is to tell what is the oxidation number of central metal iron in this complex ion. Then oxidation number of central metal iron Fe is equals to charge on the ion is 4, we have to take magnitude only, minus total charge on the ligands, See, whenever Cn is there, Cn is a negatively charged ligand, charge on this one is -1, there are 6 ligands are there, so 6 into -1 is -6, means oxidation number of Fe is -6. 4 minus of -6, here negative charge is -4. Okay, we have to take minus. So -4 plus or minus of minus is plus 6, that is equals to plus 2. So plus 2 is the oxidation number of this iron metal in this complex ion. So what we have observed from this calculation is nothing but oxidation number is nothing but the apparent charge exhibited by the metal in the complex when it is surrounded by some of the negatively charged or positively charged or neutral ligands in the complex. Means most of the cases ligands whatever discussed, they are negatively charged ligands will be observed in many of the examples we have. Hope you understand how to calculate the oxidation number of central metal in a complex. Okay, let us take another example, one more example to get an idea over it. Here I am taking example CO NaS3 6 times Cl3. So this is the complex given to us. We have to understand how its ionages to give a complex ion. So once the outside the square bracket whatever is there, the 3 chlorine atoms are there, they will convert into chloride ions. So 3 Cl minus ions, and we will be having a complex ion CO NaS3 6 times 3 plus. So what we observed is this is the complex ion. The ions which are present outside the square bracket, what we call it as coordination sphere, which are called as counter ions. Another important point we have noticed, they are counter ions, means anything present inside the parenthesis, means inside the square bracket coordination sphere, they all will be considered as ligands, but outside the square bracket or coordination sphere are present, means they are said to be ionizable, and those ions also called as counter ions. So let us talk about the complex ion. What is the complex ion we have obtained here is cobalt complex ion CO NaS3 6 times 3 plus. So in this complex ion what we have generated from this example, we have to find the oxidation number. The oxidation number of cobalt, so C is capital, O is small, that is equals to charge on the ion is 3 minus total charge on the ligands. So 6 into ammonia is a ligand which is a neutral ligand. So neutral means charge on ammonia is 0. So 6 into 0 is 0 only. So it is 3 minus 0 is 3 is plus 3 only. So that means what is the oxidation number of cobalt in this complex ion given to us is nothing but plus 3. So plus 3 is a common oxidation state exhibited by cobalt in its normal salts. Plus 2 whatever we observed for iron is also plus 2 is the oxidation state exhibited by iron in its normal salts. So what we have noticed is that but the oxidation state whatever we are calculating in the coordination complexes for the central metal, the oxidation number is common in normal salts for the metal as well as the oxidation number is same in the complex compounds. Okay, this is a common feature of central metal in the coordination complexes. So the first one coordination number we have discussed. Next oxidation number also we have discussed. Move on to the third one. Let us move on to the third one. The third one is coordination polyhedron. Coordination polyhedron. Coordination polyhedron. So this is also one of the most important information required for us to understand the geometry of the complex compound. Means the geometry or spatial arrangement, whatever we are talking, that is because of the number of ligand atoms which are present around the central metal atom in the complex coordination compound. So that we will call it as polyhedron. What is coordination polyhedron? Means it's a kind of spatial arrangement. Spatial arrangement of metal when it is attached with certain number of ligand atoms. So that means the entire geometry of the spatial arrangement of the ligand atoms attached around the central metal is said to be coordination sphere. Coordination polyhedron is said to be coordination polyhedron. Means we can decide the geometry of the complex ion or complex compound based on this point. Means when we have a particular ligand number is there around central metal, we can decide what is the geometry of that one. For example, when you are talking about ligand number, metal is there around that, number of ligands is 3. If ligand number is 4, is 5, is 6, means number of ligands like this is present, then what will be the arrangement, what will be the generally observed arrangement? So that I am just giving you. You have to remember, this is very clear in the exam. So whenever the ligand number is identified like this, arrangement 3 is there, means that is trigonal. The shape of the complex ion should be trigonal. 4 is there, tetrahedral, or it may be square planar. Tetrahedral or it may be square planar. Suppose it is 5 is there means that is trigonal bipyramidal. Trigonal bipyramidal. If it is 6 is there, then the geometry of the complex is octahedral geometry. Like this it will come. Means whenever we have tetrahedral geometry is there around the metal, these ligands will be arranged like this. Like this. This dotted line is for your observation only, that is not a bond. Thick line is only dative bond. This is the tetrahedral arrangement. Most common arrangements only I am just showing you. For example, if it is square planar is there, then the metal around that metal we have ligands present in this manner. So this is the square planar. This is square planar arrangement. This is tetrahedral arrangement. Suppose there are 5 ligands are present. 5 ligands are present means how the geometry will be there. Central metal is there. Around that, the 5 ligands are arranged in this manner. So this is the geometry of this complex when we have 5 ligands are present, trigonal bipyramidal. Not only that one, if we have 6 ligands are present around the central metal, how the complex will be visualized? Around the central metal we have 6 ligands are present. So 6 ligands when they are present, first you have to write the square planar, and after that you have to mention 2 ligands top and bottom of the square planar model. So here one, bottom side one. This is octahedral. So this is trigonal bipyramidal, this is octahedral. Octahedral, this is a trigonal bipyramidal. Trigonal bipyramidal. This is tetrahedral, square planar, trigonal bipyramidal, octahedral. Like this, these 4 different kinds of geometries we can observe when the number of ligands are present around central metal are specifically mentioned. Okay, that is about the coordination polyhedron. Okay, let us move to the next one. What I have told is next one is after coordination polyhedron, E.A.N. The most important point in the discussion of coordination complex and central metals, that is E.A.N. Expansion is nothing but effective atomic number. Effective atomic number. What is E.A.N stands for? E.A.N stands for effective atomic number. This is a theory which was introduced by Sidgwick and is spoken about the stability of the complex compounds is because of this E.A.N also noticed. Why? Because every metal, central metal in the complex compounds is involving in this formation of complex compounds and taking the electrons from the ligands for getting stability only. But the stability can be measured, means criteria for the stability of the central metals in the complex compounds is said to be E.A.N. We can say E.A.N. So I can talk about E.N, that is nothing but effective atomic number. Means it is a kind of atomic number where the next nearest noble gas electronic configuration or atomic number comes for a complex compound. After calculation, we can say that complex compound is stable. That complex compound is stable. Means metal executes the stable noble gas electronic configuration after the formation of a complex compound. That is called as effective atomic number. Effective atomic number is how we can calculate. There is a mathematical expression which is also given to us for this metal or central metal is nothing but first you must know the atomic number of the metal. That is Z is the symbol. Z of central metal atom, means atomic number of every metal whatever given in the structure in the formula must be known to us. That will be added. First we have to consider that one, we have to know that one, then we have to add some number of electrons or ions which are donated by ligands. That means number of electrons donated by ligands. So this we have to know, means whenever you know the atomic number plus number of electrons donated by ligands, we have to combine. At the same time, oxidation number of the metal also should be known to us, and that we have to subtract from this value. So number of electrons whatever is there, that we have to notice. Okay. So Z of central metal plus number of electrons donated by ligands minus oxidation number, or else you can write here only. Okay. Z of the central metal atom minus oxidation number plus number of electrons donated by ligands. Let us take an example to understand this one. So I am taking an example, that is CONH3 6 times 3 plus. This is the complex ion. So in this I should calculate what is the effective atomic number of this cobalt. Okay. So I want to calculate effective atomic number of cobalt, means I must know what is its Z value. So Z value of cobalt, first I have to notice, minus oxidation number plus number of electrons donated by ligands. This is the formula. Z of cobalt is 27 minus oxidation number of this cobalt in this complex we have already calculated. So once again for your information, cobalt oxidation number we don't know, that is X. Okay, which is equal to, the charge is equal to 3 positive plus 3 is equal to X plus number of ligands and the charge. So 6 into 0, 6 into 0 is 0. So X is equals to plus 3. That means oxidation number of this cobalt is plus 3 plus number of electrons donated by ligands. There are 6 ligands are there. These are monodentate ligands, means around cobalt there are 6 donating atoms are there, donor atoms are there. 6 will donate 12 electrons. So 6 into 2, 12 will come. So 27 minus 3 is 24 plus 6 into 2 is 12, that is equals to 36. So 36 is actually Z of next noble gas to that of the central metal cobalt is krypton. What is that? Krypton. So obviously this cobalt in this complex is reaching the next noble gas atomic number, means that atomic number is effective atomic number of this cobalt, makes this cobalt complex more stable. Therefore cobalt complex given to us is very stable, We can decide the stability of the complex compound in terms of this effective atomic number calculation. Means effective atomic number will give us an idea to understand whether the complex compound is very stable or not. Okay. So we understand this calculation. You can once again cross check the calculation part. Okay. So finally we'll do one more example by considering the negatively charged anionic complex ion to discuss about the stability. Okay. So let us take another example to find E.A.N of the complex ion. So I am considering a nickel complex NiCN 4 times 2 plus ion is there, 2 minus ion is there, sorry, 2 minus ion is there. So I want to calculate the effective atomic number of nickel, effective atomic number of nickel. So what is nickel atomic number? It is 28 minus oxidation number of nickel. So oxidation number of nickel minus 4 is equals to minus 2. So what is the oxidation number? That is 4 minus 2, that is plus 2. So oxidation number of nickel is plus 2 here in this complex, plus 4 ligands are there, all are monodentate ligands. So 4 into 2, that is 8. So 26 plus 8, how much came? 26 plus 8, 34 came. So 34 is the atomic number, effective atomic number of this complex. So this is E.A.N for this is not equals to 36 nearest noble gas, so it is not that much stable compared to the other complexes what we have discussed. So it is little unstable complex, you can say complex ion. Understand? So hope you have observed this calculation portion of effective atomic number of the central metals in the complex compound. So to find the effective atomic number, we must know Z, we must know oxidation number of the central metal, and also we must know how many electrons are donated by the ligands to the central metal in the complex. This is what we discussed in this lecture. E.A.N also completed. So these are most important points we discussed in this lecture of coordination chemistry in this session. Okay, hope you understand this session. We are going to talk many important points in the next class regarding the nomenclature of the complex compounds with the help of a table form of ligands nomenclature also in the lecture number in the fourth lecture. Okay, until have a nice day. Thank you very much.